Are we live? We good? We good, y'all? We here? We in here? We sure? We in here, right? We in here? In here like swimwear? All right, yeah. It sounds like we good. Let me turn the TV volume down. All right, bet. All right, so what's up, guys? It's Chris and Ninja here. Welcome back to study sessions. Today I am going to be going over uh ESET 462. For the final exam, the topics. I'm not actually doing the final exam. It's important to note that I'm not actually doing the final exam, professor. This is just the notes. There's no homework questions. There's no unauthorized material being produced in this. This is just like revamping the notes and uh kind of like relearning, making myself relearn, and anybody who hasn't taken the class or who will be taking the class, how y'all doing? Anyway, let's just go ahead and get into it. Um, I'm gonna be honest. I'm a little nervous. I feel like there's a lot riding on my shoulders right now. Um, so if anybody remembers, well, y'all probably might not. Y'all might remember. So uh, the first thing that we hold up. Uh, let me open another notebook. Hold up, me. I also misplaced my mouse. I don't know where my mouse is, so there's some things that will be a little more clunky today. But what I was gonna say is, for those of you who remember last time, uh, we did a study session for this class. One of the biggest things that we had to talk about was basically the basics of control systems. So basics of control systems. And to kind of summarize that, you got your closed loop. Let me move my laptop over a little bit. Y'all good? Everybody good? Y'all can hear, see everything. How's chat? Y'all good? Everybody in chat good? I'm just dropping stuff all over the floor. Yeah. Everybody all right? We good? Thumbs up, giggums. Okay. Awkward silences aside. Uh, my goodness, like why do I do this to why do I do this, bro? Like I don't. Y'all look at me like I'm supposed to know what the heck is. I'm sure I know what I'm doing. Closed loop systems. This class confuses me not because I don't understand it, but because I understand it. So the important things to know about closed loop systems. Let me brighten up my iPad so I can actually see what I'm writing. They're more accurate slash reliable. Uh, has a feedback loop, but they're more expensive. So we'll put that like more expensive and complex. Um, Compared to an open loop system. And those are the opposite. Now, if y'all are in the class with me, y'all probably like, oh, dude, why are you going over this basic? Man, hey. Whoop. This is the stuff that like the exam was told to be mostly comprehensive, like mostly the stuff from exam two, like the second half material but I want to make sure that we go over a little bit quickly of the basis of control systems. So I'm going to skip these equations. Make sure you know that. Make sure you know the graphs. So this is like the graphs of controls. So you got your output. So if you had a scroll up, make sure y'all can see that. Um, you got your output. So this is what you want. This is your desired value. Um, look the output graph. It's going to start down low and it's going to approach that. And depending on the control you have, it may reach that, it may not reach that. Um, for error, you have your how far off it is, and the error is going to decrease from there and get close to zero. A lot of times it won't actually hit zero. That's just because a lot of times you'll never actually converge to zero. And the proportional looks very similar. So like the proportional, we'll draw that in purple. Is also going to follow like a very similar trend. It might overlap a little bit. It might be a little bit different, but it's going to follow a very similar trend. Um, and this applies to any type of signal. You might have a sine wave. You might have an E signal. You never know. You never know what you're gonna have. You might have quite a few different things. I'm also gonna be like checking in, making sure that the chat isn't asking questions. If you have questions, drop them in the chat. Um, if you're in the class with me and I shared the Zoom link with y'all, feel free to tune in. You're welcome to join in at any time. Uh, yeah, so let's keep on moving then. Let's keep it rolling, keep it moving, keep it going, as Dashy would say. Um, you want to make sure you remember your Laplace transform, uh, your Laplace transform stuff. So let's just like quickly review some of that real quick. Um, we'll write the function in why am I getting so tongue tied? Like I'm gonna be honest, I am hamming it up a little bit to sound a little bit more awkward on camera, but I also don't know why I sound so nervous. Like this is just stuff that we've been doing all semester. Like I don't know why I sound so nervous. We just gonna put in the Laplace transforms here, put the function. This is stuff that you might want to put on your cheat sheet. You get a page for your cheat sheet. This is something you might want to put on there. Uh, so make the function in that color. That will make the Laplace transform, which is like make it this like that. All right. So you got your function, you got your impulse. You got your impulse function that looks like this. a little spot. It's just a spot. It happens. Just that's an impulse. See, like look. Impulse functions just like this. That's it. That's an impulse function. That has a Laplace transform of one. That's it. That's it. You got a step function. So a step function, I hope like this over the top, like performance of studying will help y'all remember during the exam. Like you'll be looking back, you'll be working on what does a step function do? What was? Oh yeah, that's right. Chris was like acting all crazy and stuff and doing all the motions and stuff like that. And this reminds me that this is a step function because he started low and he popped high and he stayed high. So like that's a step function. It starts out low, comes high. I hope this is making sense for y'all. Like I really do hope this makes sense for y'all. At the end of the day, this is still a YouTube channel, so I am trying to entertain a little bit, but this is serious actual help on how to understand stuff. Next up is our ramp function. So a ramp function goes like this, like a plane taking off. It's a ramp function. That is a Laplace transform of 1 over s squared. Then you get up to you get up to your natural function. That's your E graph. That looks like this. That would be e to the minus at. In this situation, that Laplace transform is 1 over s plus a. I'm telling y'all put this on your cheat sheets. Put this on your note sheet, man. I can't help you any more than that, man. I can't tell you anything better to do than put that on there. Like I can't help you more than that. Uh, you have your natural times a ramp function. Okay, I just want to make sure that like I want to make sure that y'all can like actually see what I'm writing because like I don't have the stream pulled up on anything really that I can. Oh, I guess I could pull it up on my phone. That would be the smart thing to do. Y'all doing all right? Y'all doing good? Everybody feeling fine? Actually see what I'm writing. Like, I don't have the stream. Yeah, you can pull it up on your phone, man. Yeah, pull it up on your phone. There we go. Now I can kind of see what's going on. I'll make sure that y'all see it. Let me zoom in a little bit more, a little far away. There we go. Yeah, it should pop up in just a second. Should get closer. Y'all should be able to see it a little bit better now. Grab the right pen first and foremost, and don't drop this pen. There we go. Um, so that would be you get your t function, you multiply that by e to the minus at. A is just some type of constant, but that Laplace transform for that one is 1 over s plus a parentheses squared. You got to make sure you square both of those. That's important to note. Square both of them. Then you get to your sine functions. Uh, so you want to make that's when you have sine of omega t. With sine omega t, you're going to get the Laplace transform of omega over s squared plus omega squared. Now, some people call it W. Not gonna lie, it's a pet peeve that I let slide all the time. I let it slide because I ain't trying to like some some of y'all is engineers, so y'all gotta remember, y'all gotta realize when it's not time to correct somebody. Like if you friends with somebody, sometimes don't correct them, man. It causes unnecessary conflict. Now, if they going into a meeting and they gonna sound like they don't know what they're talking about, then that might be a time to be, hey, bro, it's actually this. I just want, I'm looking out for you. But if you're in the comfort of your own study space, just let them say W. All right, it looks like a W. I say omega because I love saying omega. All right, I love it. I love saying it, but that's neither here nor there. Let's just get back to the work. Anyway, so that's a sine function. That's the Laplace transform for a sine function. For a cosine function, it's very similar. Make sure you don't mix these two up. It's cosine of omega t, and that comes out to be s over s squared plus omega squared. All right? All right. Make sure y'all got that down. Make sure you understand that. All right? Okay. Now you'll have a natural function times the sine function. Sometimes you'll have a natural function times the sine of the cosine function. It happens. Sometimes you get a little saucy with the math. So you get a natural times sine, which would be e to the e minus at times sine omega t. And then that Laplace transform comes out to be omega over s squared plus, excuse me, not, hold on. So omega over s plus a squared plus omega squared. Y'all got that? Now I'm sure y'all could probably guess and tell, like, somebody tell me what is the natural times cosine function? Oh, Chris, it's probably e times e to the minus at. E to the minus at times cosine of omega t. Okay, okay. And then what would that Laplace transform be? There, and Andy. Uh, but the Laplace transform would be s plus a over s plus a squared plus omega squared. Good job, Andy. Way to go. High five. Definitely wasn't me talking to myself. Um, some important notes about some important notes to take about this is that there are properties that go along with the Laplace domain. There's properties, so I will write next to this the properties. I really hope like I'm trying to make this memorable. So like when you actually go take the exam, something will stick in your head, and even if you start laughing during the exam, and I'm like, dude, what are you laughing at? You're remembering stuff. That's what it is. You just remembering stuff. So you got linearity. So everything behaves in a linear pattern. I actually got that. Shout out to Brian. Shout out to you, my man. I didn't know how to explain this. So like everything lines up in a linear fashion, or like it's continuous. You got two, the derivative. I need to hold on a second. I gotta blow my nose. Can't breathe. Oh. Okay. The derivative property. When you have s times the Laplace transform function f of s, that equals the Laplace of the derivative of f of x over time. Number 3 is the integral property. So when you have 1 over s times the function of s, that equals the Laplace of the integral of that function of x with respect to time. You have the time delay property. E to the minus s lambda, which is equal to the Laplace of this function f of t minus lambda, and that's the time delay function. And then when you have f of s plus a, so this, we'll call this the psa property. Psa. F of s plus a equals the Laplace of that function of time multiplied by e to the minus at, which also happens to equal e to the minus s lambda times f of s. So let's do a little quick example. All right. Let's have some fun with this. All right. Everybody with me? Oh, we got one like. Thank you for the like. Thank you. Welcome to the stream, everybody. Appreciate you tuning in. Thanks for being here. Let's do a quick example of this, because this, who knows, this might pop up on the exam. And if this pops up on the exam, I need $500,000. Them student loans coming back to get me. I'm kidding. I only need 400,000. No, all right. Anyway, um, so let's do an example. We'll call this example 1. Excuse the terrible handwriting, but whatever. So let's say we have a function g of x, and we want to do like 76 sine of 5t plus 8. All right, 5t plus 8. All right. Don't ask me why it's 76. You know why it's 76. Don't play dumb. You know why it's 76. That was my number in high school. All right. So with that, we know this is a time delay. So if you take a look at this right here, well, what does this look like? This right here is the same thing as what we just talked about. This is a t minus a lambda. It's a t. I mean, I know it doesn't say minus, but it's basically a t minus a lambda. All right, it's a t minus a lambda. Um, so we need to figure out what that lambda value is. So, we got 5t. Oh, oops, no. So to find lambda, we got 5t plus 8 equals 0. Well, we can do minus 8, 5t equals minus 8, divide by 5, divide by 5. Then we get t equals 8/5. 8/5. All right. So we got 8/5. you know what? I don't like these numbers. I want these numbers to be nicer. We're gonna back up. We're gonna back up. We're gonna make this 5t and 5. All right. We're gonna back up a little bit. Just bear with me. I don't feel like doing extreme heavy calculations. We got a lot more to go through. This is just an example. All right, just an example. So basically, t equals 1. Well, actually, no, we'll do 10. We'll do 10. We'll do 10. Sorry, y'all. I keep changing the problem. Okay. So, algebra, you get minus 10 equals 5t, divide by 5, t equals 2. All right. So t equals 2. T equals 2. All right. So, uh, so you pull out 5. So then you end up having 76 sine of 5 times t t minus 2, negative 2. Yeah. Yeah. Well, it would technically be plus 2 because like just don't worry about it. We'll say it. We'll don't worry about it. It all works out later in the math. All right, it works out later in the math. So then, if I had do the inverse Laplace of this, we get 76 just hanging out on the side of things. And then that's multiplied by omega, which is in this case 5. Omega is 5. Yeah, omega is 5. So we get 5 over, oh geez, this is not writing. Get 5 over uh s squared plus 25. All right, all right. So then we're trying to figure out like where that what the junk the e to the e value is going to be, because there's going to be an e value in this as well. Um, so the lambda value that we found ends up being 2. So lambda equals 2. Yeah, lambda equals 2. See, I told you the math was going to work out. So then we end up having this multiplied by e to the minus 2s. Yeah, e to the minus 2s. Well, no, e to the 2s because it's minus 2, because the lambda is the lambda is the minus 2. Okay, we got this. We got this. Yes. Um. Well, so then the final answer ends up being 7. Oh, geez. Final answer ends up being 76 e to the minus to the 2s times 5 divided by s squared plus 25. All right. All right. Cool. Cool. Everybody cool with that? See. See. You can simplify that down a little bit more. You'd get uh 30, 38, 380. I think that simplifies down to 380 e to the 2s over s squared plus 25. But that's just an example problem. That's an example that can be done. If you want to do one, that's an example you can do. Um, let's see, let's see. So Also, another thing you might want to put on your cheat sheet, whenever you're converting a transfer function, whenever you're converting a transfer function, most of the time you'll have y over s, or y of s over r of s. Some form of y of s, some form of some form of y of s, some form of r of s. That is always um gonna be like a g times u over 1 plus g times u. All right. So just making sure I don't skip over anything that's actually like really important. Uh so one of the things that was not on the last exam that will be on this exam, um, or that will probably be on this exam, is the concept of complex and repeated real roots when it comes to when it comes to the inverse Laplace transforming. So let's write some notes about that now. Let's get it cracking. And I ain't talking sea monsters. I'll stop. I'll stop. No, no, y'all don't have to tell me. I got it. I get the message. I got it. Okay, so inverse Laplace transform. So with inverse Laplace transform, oh, any questions, by the way? Any questions so far? No questions in the chat? Nobody asking anything? Y'all good? Everybody got it? I'll give y'all a second. Any questions? Put them in the chat. Um, and if anyone has questions, feel free to ask. Give y'all a minute to process all that. It's a lot of brain to process. No questions? Let's see. Okay, so if you go back and check on lecture 56, it might be a little different if you're in a different class, but essentially there's a process. I'm gonna like move. Hold on a second, y'all. I'm gonna make this a flat surface so y'all don't have to like get sick watching my face go like this. So I crack my neck. Anyway, um, so inverse Laplace transform. Sometimes you'll have repeated real roots. So the example that I can give us from let's do an example. An example seems like a good way to kind of introduce this and kind of reteach it a little bit. So let's say I have like I don't know, S plus 7 over S plus 1 times S plus 4 squared, right? Some simple, some slight, right? Well, we know that the roots of this is going to be at S plus 1. So we know the root. Let's go back to the roots. There's kids. Okay, let me stop. My friend Bree tells me all the time I get easily distracted. She's so right. It's because I don't have anybody like to study with, like actually right here. I just have like chaotic energy and I don't have anything to like direct my focus to. But that's beside the point. So we know the roots on this are going to be at S1, S plus 1, and S plus 4, and S plus 4. Well, what the jump, man? Like hot cheese it, bro. What are we supposed to do, man? We got two of the same number. It doesn't make sense. You can't have two of the same number. That I got you. Don't worry. Don't even trip. Don't even trip, dog. So one might think, and this is the wrong way to do it. So keep in mind, this is the wrong way. So wrong way. One might think you just do C1 over S plus 1 plus C2 over S plus 4 squared, right? And then you go do your math and then you get like some type of long answer. And then no, that's not how you do it. That's the wrong answer. You'll get the wrong answer every single time. That's not correct. All right. It's not correct. Okay. All right. We all understand each other. We got it. Y'all understand what I'm talking about? This is how we do it. All right. All right. Look. I'm gonna teach it to you real. I'm gonna teach it to you real simple. All right. This is the correct way. All right. Here we go. I'd say buy my tape, but I don't have a tape. I just have a YouTube channel. Um. So you got your S plus, what was it? S plus 7. You got your S plus 7 on top. You got your S plus 1, and you got your S plus 6 squared, right? Or S plus 4 squared. My bad. So you're gonna so just like we did with the regular non-repeated roots, the distinct real roots, we're gonna break this up into its components. That's what we gotta do. We gotta break it up into components, okay? So we're gonna break this up into C over C1 over S plus 1 plus C2 over S plus 4 plus C3 over S plus 4 squared. You see what I did? Oh, hold on, we can't see it. You see what I did there? There we go. There we go. Yeah, see. Let me let the chat catch up a little bit. Y'all are like on an 8 second delay, so I got to give y'all a little bit of time to adjust and catch up and everything. By the way, this is part one. This is part one. So this is part one of the full study review session. I'm gonna do like 3 or 4 topics in this one, and I'll do 3 or 4 topics in the next one, and we'll call it ready for the test. Ready to go. I don't know why I'm stuttering so much. So unfortunately, because these are repeated real roots, there's not really a fast way to do this. Like there's no fast way to do this. All right. So what you gotta do? Here's what you gotta do. You gotta get everything to be the same denominator. You gotta get a common denominator so you can add all the C1, C2, C3 all up with each other. So if you notice here, we got if you notice here, let's spread this out. Let's spread this out a little bit. I had to make a little scribble over there so I could spread it out a little bit. So let's spread out. And let's do these in different colors, all right? Let's do some different colors. Let's have some fun. I know nobody's having fun because this is a highly heavy in math, but let's try to have some fun, all right? So we got C1 over S plus 1. Well, we know C1 is missing an S plus 4 squared. So we got to multiply by s plus 4 squared over s plus 4 squared. We know that we're missing, so we got that added. Put that back in blue. So we know we got a C2 over S plus 4. Well, we know that's missing an S plus 1 and an S plus 4. So we got to multiply by both of them. We got to multiply by both of them to get that common denominator. We need to multiply by S plus 4 times S plus 1 over S plus 4 times S plus 1. All right, see, look, nice and simple. Nice and simple. We keeping it simple, all right? Keeping it real simple. The next thing we do is we got C3. C3 over S plus 4 squared. Now we know C3, all it's missing is S plus 1. So we just got to do S plus 1 and S plus 1. All right. So now we get down to the algebra of the situation. Okay, here's the situation. We got to break down the algebraic equation. I don't know how I freaking pulled that from parents, just don't understand. Shout out to you if you know that song. So we know that we're going to end up having C1 we're going to have C1 times S plus 4 squared over S plus 1 times S plus 4 squared. That's going to be added to. So that's plus C2 times S plus 4 times S plus 1 over S plus 1. Well, let me write those all in the same denominator. All the denominators in the same color. S plus 1 times S plus 4 squared. The reason I'm writing all the denominators. Oh, y'all cannot see that. The reason I'm writing all the denominators in the same equation is so that way we can see that they're all common denominators. Because I mean, like, I'm not the greatest algebra person. Algebra confuses me sometimes, especially when it gets like all these symbols and stuff. But seeing it like this, I can visualize that these are the same number. These are the same thing. All right. So then you add that to C3, your C3 value, and that's C3 times S plus 1 over, and once again, that's a common denominator, S plus 1 times S plus 4 squared. All right. All right. So we got, everybody got that. Everybody cool? No question in the chat. Chat got any questions? Chat questions? Any questions in the chat? Chat? No chat questions. But Chris, how do we solve this? I'm glad you asked that, Andrew and Andy. That's the name I use it for, right? Andy, I'm glad you asked that question. We solved this by breaking it down. Now, see, it might take you a minute because it might take me a minute, but you might have this off the dome. I don't always have this off the dome. And this is not an actual problem that we did. So I got to like kind of redo it. And I'm making up a problem off of a problem that I made up before. That's beside the point. The point being, let's take a short little field trip to solve some equations. So we know we got it's gonna pop up. Okay, that's where it is. Okay, so we know we got S plus 4 squared. That breaks down into S squared plus 8S plus 16, right? S squared plus 8S plus 16. That's what that breaks down into, correct? I think I'm right. I think I'm correct. It would have been really embarrassing if I was muted this whole time. I just know I'm not muted because I can hear my voice. And then we got S plus 1 times S plus 4. That breaks into S squared plus 5S. Oh, geez, I need to write more neat. That breaks down into S squared plus 5S plus 4. All right, so we got some nice, simple, nice, beautiful numbers. Some beautiful numbers right here. You see that? Look, that's the thing. They should put that on the front of cars. If I had a nickel for every joke that I stole from another grade. Okay, so now we know we got C1. Let's do this in a different color. Let's do pink. Let's do pink. C1 times S squared plus 8S plus 16. All right. Also, since we have all common denominators, we can just kind of basically say like, this kind of doesn't matter. Kinda. Oh, y'all need to see this. I'm sorry, y'all. I be forgetting to scroll. Like this matters, but like not important anymore. Because we have a common denominator. So we're basically just doing addition. We're basically just doing addition and multiplication. It doesn't really matter what they are right now. We're just trying to solve. We're trying to solve everything together, and we know that this whole thing. We know that this whole thing. This is equal to our original equation of S plus 7 over S plus 1 times S plus 4 squared. Because those are the same denominator. We know this. We know this. We know for a fact that that's the same thing. So that's why I say it doesn't really matter too much right now. It doesn't matter too much right now because it equals the same thing. So it's going to end up being the same thing regardless. So now we have that, and then we're adding C2 times S squared plus 5S plus 4. And then you got C3 C3 times S plus 1. Nice and simple. Pretty simple. So then you just so like our professor, he doesn't really go through a lot of the algebra steps. So I know some people get tripped up on the algebra. This is just like if you know you do the algebra right, this is like a double check. Make sure I do it right. So we got we're just combining like terms. So we know we got an S squared and an S squared going to a C1 and a C2. So let's group them together. So we got an S squared here and an S squared here. So we got S squared times C1 plus C2. Now let's add up our S's. Let's get our S's together. So we got an 8S here, we got a 5S here, and we got one S here. So we know we have S times C1 or 8 C1s plus 5 C2s plus 1 C3. And then as our constants, we'll just do those in we'll keep those in like this blue, like it's cyan. We just got 16 C1 plus 4C2 plus C3. All right. Okay, so that's a lot of numbers. That's a lot of numbers. But here's where it gets real simple, right? So we know that there's no S squared. So if we take a look back up here at this equation right here, we take a look up here. I don't know if y'all can see that. Y'all can't see that at all. Take a look right there. What do you see? You see an S plus 7. But if you notice what's missing, we're missing an S squared. There is no S squared. So we know that this term has to go to 0. We know that there's one S, so there's only one S. So we know that this term goes to 1. And then we got 7 left as the constant. So we know that this altogether equals 7. All right. So that's how we can break that down. Welcome to the stream. Thanks for being here. I just noticed that you tuned in. Welcome to the stream. Thanks for being here. Appreciate you. Appreciate big preach. So we know that C1 plus C2 equals 0. We know that 8C1 plus 5C2 plus C3 equals 1. And we know that 16C1 plus 4C2 plus C3 equals 7. Well, now this is the easy part. This is that easy stuff right here. Kinda. Just don't mess up the math. So we know that C1 is equal to negative C2. Just off rip. We know that to be a fact. So if we now substitute in oh, frick. Oh, there we go. Okay, awesome. Oh, okay. Okay. So let's say we plug in for C2 we put minus C1 or yeah, let's say we put minus C1. So now we have 16 minus 4. That gives us 12. So 12C1 plus C3 equals 7. And then if we want to make C3 equal something in terms of C1, we know that C3 equals 7 minus 12C1. I just want to make sure I'm doing this right. Yeah. Yeah, I think this is the one, right? Yeah. Yeah. Okay, so then, sorry, y'all, I was just checking my math. Sorry for the silence. Just checking my math. Then if we take this and then insert that here, so we insert that there, and then we got we no longer have plus 5C2, we have minus 5C1, minus 5C1, because it's the negative, because C1 is negative C2. It doesn't really matter which one you use, but and then we know that C3, well, we put C3, if we plug in 7 minus 12 C1, and that equals 1. All we got to do now is just solve. So we got 8 minus 5. That gives us 3C1 minus 12C1 plus 7 equals 1. So that means minus 9C1 plus 7 equals 1. Minus 7, that gives us negative 6. Negative 9C1 divided by 9, divided by 9. C1 equals equals 2/3. C1 equals 2/3. Because 6/9 is 2/3. That means that C2 equals negative 2/3. And then if you do you do 12 times 2/3 plus C3 equals 7. Then just calculate, use a calculator real quick. 12 times 2, 3, 8 is 8 plus C3 equals 7. So then C3 equals minus 1. So finding that C3, so finding that C1, C2, and C3. So we got our numbers. C1 equals 2/3, C2 equals minus 2/3, and C3 equals minus 1. Uh, we now just have to put them in with our we just now have to plug them into our originals, our original C equations, the C equations that we had. Just got to plug those back in real quick, and then that would be 2/3 times 1/s+1 plus, or minus 2/3, excuse me, minus 2/3 times 1/s+4, and then that is also minus 1/s+4 squared. Now, this is the easy part. This is the real easy part right here now. Come on now. Come on now, boy. Come on now, boss. Come on, dogs. Come on now, dogs. You know what we're doing here. You know what to do. You inverse Laplace, right? I'm looking up here because my camera is normally up here, but like the camera for the stream for this one is right here. y'all can tell, like I sit at this spot all the time. So anyway, so you end up having your final answer. We'll do this in green, like a nice lime green. So you get 2/3. Y'all can see that, right? I hope y'all can you see that? Can we chat? Can y'all see it? Y'all can't see it yet. I'm gonna give it a second. Oh yeah, okay, there we go. We can see it. I I can see it on the screen. Let me zoom in a little bit. So you got 2/3 times e to the minus t, because the a in this is a 1 minus, or yeah, minus 2/3 times e to the minus 4t, and that's minus uh t times e to the minus 4t as well. Yeah, minus 4t as well. And that's the final answer. That's how you do repeated real roots. So just follow that same process. That's how you do repeated real. So this is a repeated real roots. Any questions? Any questions in the chat? Anybody got questions? Taking questions, live questions. Oh, no questions? Everybody good? You got your snacks? You study snacks? Got them fruit snacks? Gummy bears? Ugh. Okay, so um, I'm reading back over these notes real quick, make sure I understand what I'm supposed to do here. Uh, okay. Wow. Started an hour ago. Um, take. Let me take a shot of water real quick. Take a water shot. Get a shot of water. Tough loss yesterday for the Aggies. How about them Cowboys? No, Cowboys won today. My eyes are getting tired. Like I'm stalling for time. Okay, let's get back into let's snap back to reality. All right, let's snap back to it. All right. Okay. So let's say we got like what happens if we have complex roots? Like, is it possible to have complex roots? So let's do like so with complex roots, it's a little bit different. Let's do a little bit more of a spicy example. Let's do a spicy example. Let's do like 4s squared minus 36. 4s squared minus 36. All right. Let's do that. And then we'll do that over uh s minus 5 times s squared plus 12. Well, we'll do we'll do 25. We'll do 25. S minus 5, S squared plus 25. Now, y'all might be thinking, the freak, why is this not, hey, yeah, you better update. Yeah, yeah, uh-huh. Sometimes just gotta like, get aggressive with your technology now. Um, so we're trying to find GOT. So let's see. We're trying to find this. The inverse Laplace of this equals GOT. All right, that's what we're trying to find. So how the heck do we do this? Well, we do the same start the same process. Everything starts out exactly the same way. We always got to start out the same way. Consistency is key. So we already know we got to break this up into the C1, C2, C3 because we got three roots. Now you might be like, oh, if you don't open your eyes. You see the S squared there? I don't know why I'm pointing at the TV like you can see it, but you see the S squared? Do you see this S squared here? Do you see that right there? That means it's the third root, okay? All right, look. I wasn't trying to get mad at you. I ain't yelling at you. I'm just going a little crazy studying for this stuff. All right. Anyway. Um. So we got three roots. So we got a C1 plus a C2 plus a C3. Now you might be like, "Hey, bro, what exactly are we supposed to be doing here? We got to get an S. Well, here's what we got. We got an S minus 5 over an S plus 25, and that's over an S squared plus 25. Now, this is not the easiest thing in the world. You can't just throw this you can't just throw this junk around like it's just magic, bro. You got to step one, you got to determine the root. Step one, determine the roots. So you got to figure out what your roots are. Well, how do you figure the roots out for this? You don't have anything simple. You don't have anything simplistic to figure out, man. This ain't Like it feels like it's rocket science almost. In a way, kinda. It kind of feels like rocket science, don't it? Kind of does feel a little bit like rocket science. Well, here's one of them. Here's I'll tell you what one is. All right, I'll give y'all a hint. I'll give y'all a little sauce. S1 is equal to 5. All right. There you go. There. Y'all got the rest. Y'all ain't got the rest. That's why you're here. You're here because you don't have the rest. Here's the rest of the problem. So for this, you need to do the quadratic equation. Now you might be thinking, I haven't done the quadratic equation since I was 13 years old, and that's exactly what I thought until about 2 weeks ago. Then that's the last time I did the quadratic equation. So you're gonna have to take your if you don't remember, it's minus b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. All right. This is the quadratic equation. It gives you the roots of any quadratic equation. All right. Well, in this case, I don't know about you, but I don't see a B. I don't see a B anywhere. I see an S. I do not see a B. I don't see a B. So that means that B is, in this case, is 0 plus or minus the square root of 0 squared minus 4. Well, we know that A is 1 because A goes in front of the squared because this quadratic formula. So just a quick review. You'll have an A times x squared plus a b times x plus a c, which is the constant. So I don't see a b. So the b's missing. The b's out the equation. The b got booted from the island. All right. You got so you got 0 plus or minus the square root of 0 squared minus 4 times, well, a is 1 because a is just the 1 in front of the s. And then we know that c is 25. So we got 25. So 4 times 25. Well, 4 times 25, that's 100. That's a fat 100. That's 100 right there. You know what I mean? Hey, hey, that's what it is. What it is, and that's all over 2. So that ends up being plus or minus the square root of negative 100 over 2. Which, if you pull the negative out and just make that an imaginary number, so you got like square root of negative 1, you end up having 10 over 2, which is 5 negative 1, 5 times the square root, 5 times the square root of negative 1. Or as engineers like to call that, 5J. What did I click that for? Yeah, it's 5. So we got plus or minus 5J. So our S2 roots, so going back over here, back to the roots, plus 5J, and S3 is minus 5J. All right. So now, oh geez. Well, now you might be thinking like, well, Chris, there's no like regular Laplace transform that can deal with any imaginary roots. What are we to do? Well, concerned viewer, who was me? I got you. So in this event, we got to use something that can handle imaginary values, like an omega, because we gotta if you remember, you gotta you gotta have a let me just do this step by step because I'm messing myself up. So step two, split into functions. And we need an A and an omega. Oh, I remember. I remember now. My goofy self, man. I remember now. So if you remember back when I was talking about like the imaginary plane and everything like that, and how like basically all the numbers are in the fourth dimension and blah blah blah, and a bunch of stuff that nobody actually watched and paid attention to, you'll remember that you have basically some equation in electronics that ends up being like A plus omega I, some or omega J. That's like your phase. That's when you get the phase angles and stuff like that. So when you have things that are going in and out of phase, you have a real value, which is this A value. So and you have your imaginary multiplied by an angle omega. So when we split this into equations, we need something that has an omega value in it. That's what I was trying to look for. That's what I was looking for that I kind of forgot about. So you got a C1 over S minus 4, the freaking cheese crackers. S minus 5, excuse me, S minus 5. Plus, you need a C2, got a C2, and that's multiplied by one of our omega functions. So we'll just say that's omega. I need to write the denominator first because if not, I'm going to draw this bad. Also, I'm not sick. My nose just be running. Promise I'm not sick. We got F, oh geez, got S plus A squared, and we want to make sure we use the S plus A squared version because there's a chance we don't know. Like you really don't know what the freak is going on here yet. You don't know what's going on here. If we're being completely honest, you're taking a shot in the dark. You're like Michael Jordan before he got good at basketball. All right, you're on the court, but you don't know where you're shooting at. So you got to make sure you account for it in case there's a natural function or if there's like some type of time shift or something. You got to account for that. And then you add that to omega squared. You put that, you put an omega over that, and that's one function that we're multiplying by C2. Then we got our C3 value. I'm going to do that in a slightly different color. So plus C3. And then you gotta multiply that by the S plus A over S plus A squared plus omega squared. All right, so we got to determine what A and omega are. So that's step three. Step three. You got to know what A and omega are because if you don't know what A and omega are, you're not going to get any kind of answer that's going to make any sense. It's not going to make sense, and I can promise you that. I'd bet you $5 it wouldn't make sense if you don't know what A and omega are. So just to spice things up, we're gonna get a little different shade of purple, you know what I'm saying? So we know that A is the real part. So A is our real part. And we know omega is our imaginary part. So in this event, we didn't have an A value because there was no real part. If we look at the equation, in this particular event, we didn't have an A part. So the A plus omega, so the A plus omega J. We didn't have one. So this, there is no A value. So S plus A just equals S. Anybody got questions about that? Do I need to, I'm gonna pause right here to let anybody who has questions about this ask their questions. Because this is something that might go over. Somebody said they might have been like, oh, what, huh? What S plus A equals S? No, 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 no. Anybody got any questions? Do I need to explain this any further? Please let me know. Please tell me now. Please. Chat, comment section. Anybody, please. I'm watching the chat. Like, let me refresh the chat real quick. I'm watching the chat. Anybody? No questions. I'm gonna give y'all like 15 more seconds. I want to make sure that no one has questions about this. I want to make sure that I'm clear. We only have S plus A equals S because A is zero in this case. A is not always zero, but in this case, A is zero. Everybody cool on that. Everybody got that? We all Gucci down to the socks. Okay. Okay, so boom. Big Shaq, hold tight. So we know that omega, so it's also important to note that when you're writing down these equations, that omega is just the number. It's just this part. It's just this part. Omega equals 2. Leave the J slash I. Leave the J slash I off. I wanted to make sure that all the questions there were no questions being asked. So now we're on to step 4. So here's step 4. We know that we have C1 over S minus 5 plus we know our omega value. Our omega value is not 2. Our omega value is 5. Look, don't clown me. Don't clown me. I'm reading off of an example because this is how I study. Our omega value is 5, so we got 5C2 over S squared plus 4, or S squared plus 5, I mean. S squared plus 25. And then we got SC3 over S squared plus 25. 25. If I could write, gosh dang, man. So we got those values coming in. So fortunately for us, now that we have fortunately for us, now that we have these are the same value, we can do a little bit of magic. So you have 5C2 plus SC3 over S squared plus 25 plus C1 over S minus 5. We multiply both sides. We have to multiply by both sides by the values to get the common denominators. So we have 5C2. Oh, y'all cannot see this. I apologize. I forget to scroll up because I have it on my iPad and I don't be looking. 5C2 plus SC3 S squared plus 25 times S minus 5 over S minus 5. That equals 5C2 S five C2 S minus 25 C2 minus 5 C3 S plus S squared C3. I think that's right. I might have done that a little bit backwards, like out of order that a lot of people normally do it, but I believe that is correct. And then we have C1 times S squared plus 25. Let's just go S squared C1 plus 25 C1. And that equation ends up being altogether C1. Let me do this in a brighter color. Oh, I did not realize how far away I was like actually writing. So altogether we have C1 plus C3 S squared. Yeah, C3 S squared plus 5C2S. Well, 5C2 plus or minus 5 3CS plus 25C2 plus 25C1. Great. Now we can break this down a little bit further because this is supposed to equal, at the beginning of the problem, 4s squared minus 36. Four s squared minus 36. Oh man. So if you notice here that this s term will go to 0, so we know that 5C2 minus 5C3 equals 0, which means that C2 equals C3. Because if you do the algebra, it equals that. C1 plus C3 equals 4. And then 25C2 plus 25C3, or C1, 25C2 plus 25C1 equals 36. These are some odd numbers. We're gonna make it work now. All right, here we go. Here we go. All right, here we go. Like that Prescott. Yeah, here we go. I think I did this right. All right. Oops. So with C2 equaling C3, that going to 0. I can do 25C3 equals oh, well, I gotta get sorry, y'all. I forgot how to math for a second. It's been a very, very long stream so far. So, so I can make C1 equals 4 minus C3. If C2 and C3 are equal to each other, then I know that 25C2 is also equal to 25C3. And then I can do 25 times 4 minus C3 equals 36. So that I have 100 minus 25 C3 equals 36 plus that C3. So then that's not adding up. Some's not adding up. I think I made a math mistake. Hold up. Something's not adding up. Oh, there we go. I found it. I found it. Bro, what the, bro, I was trying to say this video is private. This video ain't private, is it? My mistake. See, this is why you do math. This is why you do math slowly, because you catch stuff like that. I forgot that this is a minus 25 here. This is a minus. So that makes that a minus. So then minus minus. This is technically a minus as well because it's negative 36 because it's minus 36. This is a minus and this is a minus. But anyway, so you minus 100. So you get a minus 136 equals minus 25 C3 minus 25 C3 minus 50 C3 equals minus 136 C3 after you divide by 50 on both sides. See, I knew there was a math mistake somewhere because it wasn't making sense. Math wasn't mathing. So you can just say C is 136 over 50. Or you could say like 68 over 25. Okay. So with 68 over 25 being our C3 value, we know that C2, so C3 equals 68 over 25. C2 is also, and then let me do this on the thing real quick. So we got C1 equal to 168 over 25. So that's what we got there. Those are our values. Okay. All right. Now, I wish I picked nicer numbers, but it doesn't really matter in general. You just now go to, excuse me. Excuse me. I'm sorry. Now you just go to, uh, now, hold on a second. All right, there we go. My voice sounds better now. Sounds very instructional. So the numbers don't really matter all that much. All that really matters is that we have our values that we can multiply by. So we'll say 168 say 168 over 25 multiplied by 1 over s plus or s minus 5 plus 68 over 25 multiplied by 1 over s squared plus, or I guess it'll be 5 over s squared plus 25. And then you'd have plus 68 over 25. Let me that over a little bit. And we'll change that to that purple color. 68 over 25 times S over S squared plus 25. When we're doing the when we do the inverse Laplace transform for that, we'll end up having 168 over 25 E to the 5t, because the minus 5 turns to a positive because it's minus t minus at, plus sine 5 sine, or wait, no, it would be 68 over 25 sine of 5t plus 68 over 25 cosine of 5t. So that's how you do a complex real root, or that's how you do complex roots. This complex roots of inverse Laplace transform. All right, let me see what the other topics are that we gotta cover. Um, Honestly, let's see if I can cover the first order analysis. This has been a long stream. Like, well, it hasn't been a long stream. It's just been like a lot of heavy math. Like, it's been heavy math. So let me look at the summary one more time. Um, Second order systems. Okay, so yeah, let's just do a quick thing over the final value theorem. Um, it's kind of review because I think this was on the last exam as well, but it wasn't really as deeply covered. Sorry, y'all. Just give me a sec. Ugh. All right. Oh yeah, we're locked in. Oh yeah, we're back. We're back, bro. We're good. We're rocking. We're rocking and rolling. So let's do a quick thing about the final value theorem. So if y of t, hey, you should follow my yt. No, no. Oh, okay. Y of t has a final value. The final value of yt can is the limit of y of t, and that is as the limit as s um as t approaches infinity as t approaches infinity of y of s times s at s equals 0. Oh. So this is the final value theorem. It does not, so it only applies. It's important to note that this only applies to systems that converge or, in other words, are stable. That means sine waves, exponentials, cosine waves, ramps, or any function that does not end. They can't do the final value theorem. No final value theorem for them. Sorry, not sorry. So let's just do a couple examples real quick. Let's do some examples. Because it'll help. The examples really help me explain what I'm like. Explaining how I'm working through the problem is what the study session is really about. It's about no, it's about knowing how to do what you're working on. So let's say I have a system. Let's say I have a system like this. I got a U, and I'm look, Bree, shout out to you. I'm gonna try to make you jealous. I got this. I got a U. Let's say I got like a 12 over 4s plus 6. And then I have an output y. You jealous of my box? Cause I drew the box. No, you're a real one though. Look, shout out to Bree. She a real homie. I don't think she would be mad at me teasing her a little bit. She's awesome though. So time constant. So in order to have a final value theorem, you need a time constant. So the time constant for the final value. That will be a tau value. That is equal to B2 over B3. To make things easier, B2, B3. So our time constant is 4 over 6, which equals 0.333, or not 3 point. I'm trying to think if I want to actually use this or not. If I want to have like a nice number, like one that'll actually stop. Uh, let's do 12. Yeah, let's change this up and let's do 12. So we'll do 4 over 12. That is 0.25. No, no. God, freaking gosh, dang it. Picking all these repeating values, man. Dang it. New frick 4 and 12. We're doing it my way. Doing it my way. 3 and 4. 3S and 4. Gosh dang it. Divide 3 by 4. You get 0.75. There you go. Cheese, bro. Okay, I'm not gonna rage quit yet. I can't rage quit yet. Being a teacher is hard. Trying to teach this stuff. So also let's say that there's a ramp function, or not a ramp, step function of 5. Step function with the magnitude of 5. Jumps up to 5. So what we got to do, here's how we crack a lack it and smack it. All right. So we know that U of S. So yeah, U of S is equal to 5 over S. All right. Y of S Y of S is equal to 12 over 3S plus 4 times U of S. Now, it's very important that you don't forget this. Do not forget this. If you forget this, you will make a mistake and get the problem wrong. All right? Don't make the mistake and get the problem wrong, okay? All right? Look, I'm trying to save you from yourself, all right? Listen to Coach Ninja. Listen to Coach. Listen to Coach. All right, look, see, when I'm out here coaching football and being a math teacher or something like that, they're gonna come at me like, "Hey, Coach Carter, Coach Casey, oh, I don't just write what I tell you to write. All right, do the thing like I'm telling you to do it. You're gonna be fine. All right, you're gonna be fine. All right, okay, cool. We all good. Everybody got that. Jarrell, yeah, Jarrell got it. All right. You know, Jarrell likes to misrun routes. Makes Coach Saban pretty angry. So with the Y of S, we end up having 12 over 3S plus 4 times 5 over S. Oh, freaking gosh, heckin' cheese. Not now, iPad. So in order to solve this for the final value theorem, we need to take the limit. So we need to take, so for final value theorem for FVT, we need to take the limit as t approaches infinity of y of s multiplied by s at s equals 0. Now you might be like, "Hey, bro, what is it supposed to be, man? What do I do, man? I got you, dog. I got y'all. I got you. It's easy. Same y of s that you just had up there, the 12 over 3s plus 4. So you got 12 over 3s plus 4 multiplied by 5 over s multiplied by s. It's simple like that. Just simple like that. All right. Keep it simple. Don't do anything extra complicated. All right. Keep it simple. Don't complicate yourself now. Now make it even more simple for you. This s and this s cancel. And then this is at s equals 0. So that s and that s cancel. So the only s that equals 0 is this one. The only one that really matters is this one. So you got 12 over 3 times 0 plus 4. And that equals 12 over 0 plus 4, which equals 12 over 4, which equals 3. The final value of this problem is 3. So let's do one more example. Do one more example and we'll call it for the day. Because we've been streaming for like 2 hours at this point. I think we've been streaming for like 2 hours. People starting to get bored. People starting to tune out. But it's okay. It's your grade. It's your grade. Last thing we're going to do this one right here. So we want the final value theorem. Say we got an R that goes into this plus, so minus here. We got our error that goes into 4, that goes into our U value. 2 over s plus 4. Get our y out, and then this is our feedback coming back there. So first thing you need to do is you need to get the closed loop transfer function. With the closed loop transfer function, you will have y of s, like I said before, equals that ends up being 4 times 2 over s plus 4 over 1 plus 2 times 1 plus 4 times 2 over S plus 4. That ends up coming out to 8 over S plus 4 over 8, 1 plus 8 over S plus 4. And then that's multiplied by RS. Um, oh, freaking cheese, man. Cheese crackers, man. If I remember how to break this up, break this into what I needed to. Nope, don't remember. So that's a like tomorrow stream problem. So we got the limit as t approaches infinity, y of s times s, which is 8 over s plus 4. Oh, by the way, this is at s equals 0 over 1 plus 8 over s plus 4 times, we'll just say that the ramp function again is 5, so 5 over s times s. This cancels, and this is at s equals 0. So we can do this. We can do this the way that I think would make it a lot easier to solve, and make s equals 0 first. So then we have 8 over 4 over 1 plus 8 over 4, which equals 2 over 2, 3 times 5. That equals 10 over 3. And then for the steady state error, then you will have r minus y. So e at time equals infinity equals r at t equals infinity minus y at t equals infinity, which ends up being, well, r is constant. The r is a constant, constant 5. Yeah, this makes r 3, I think. So we got 5 minus 10 thirds equals 15 over 3 minus 10 over 3 equals 5 over 3. So the steady state error And there we go. So I'll do a little bit more. I'll do a more complex one in the next video. Um, yeah, I'll do a more complex one in the next video, and then summarize the time constant theorem, final value theorem, and stuff like that. Um, and then we'll hop into the next topic. So we'll start out with something very similar to this. So let's see. This is but yeah. So with all that being said, I'm tired. I think it's a good stopping point. Um, yeah, we'll just stop right there. Uh, so I just want to say thank you guys. Oh, hold on, let me go. Ready to, yeah. I want to say thank you guys so much for watching this video on the stream. If you liked it, strike that like button like a ninja really would. Subscribe today to join the Shinobi, and I will see all you guys